Okay, so we're going to talk about vaporization. Vaporization is the change from a liquid into a gas. And we're familiar with that happening like when water is boiling, but it also happens at lower temperatures. So here we have an illustration of a beaker of water. And the molecules in the liquid water are in constant motion. And this is where that Hoffman quote comes in. It's a wild dance floor there at the molecular level. This is like a mosh pit or something. It's just teeming with activity. Molecules are vibrating in place. They're spinning around. They're moving relative to each other. It's just crazy. So in an open beaker, there are molecules that are at the surface, and then most of them, of course, are down on the interior. If a molecule that's at the surface has enough kinetic energy to break away from the intermolecular forces holding it to the other molecules, it can escape into the gas phase. Does that make sense? So these molecules are going off into the gas phase. So most of these are probably going to escape because this is an open container. But there's also water molecules present in the air because there's always some level of humidity. And so a water molecule from the air in the gas state could have a collision course with the surface of the water. And when it hits the water, it's going to get trapped, captured by the intermolecular forces. And so we have things going both directions. We have vaporization, which is transition from liquid to gas. We also have condensation, which is the transition from gas to liquid. So I like to think of the surface here as being like a game of Red Rover. You guys know that game? They don't let kids play that in school anymore because, well, if you know the game, you can see why people can get hurt. It's a good way to break your wrist. But for those of you that don't know, you have two groups of children on opposite sides of hopefully a grassy field, and they make two lines and they hold hands. And then somebody, a bossy person on one team, says, Red Rover, send Sally right over. He's calling out somebody on the other team. And they let go of their line and they run across the field at your line and they try to break through your hands, right? And so are they going to make it through or not? Sometimes they do, sometimes they don't. What are the factors that determine whether they're going to break through the line? Inertia or momentum, how fast the person's going, how much they weigh, how strong the bonds are, yeah. How strong is the grip of these people? And if Sally's smart, she knows who of her classmates are wimpy, and she's going to go for them instead of the tough guys, right? Because it's easier to break through when the grip is weak, okay? So those are the same sorts of ideas that affect vaporization of a liquid. The intermolecular forces are the children holding hands. And if their grip is strong, if the intermolecular forces are strong, it's harder to break through. A molecule coming to the surface, will it break through or not? Well, it depends on how much energy it has. Does it have enough kinetic energy? 1/2 mv squared, mass times the velocity squared. If it's bigger, it'll have more kinetic energy. If it's moving faster, it has more kinetic energy. And the kinetic energy there is dependent on or related to the temperature, right? The temperature of the liquid is the average, is a measure of the average kinetic energy. So if we have a molecule at the surface that has enough energy, it can break through the Red Rover line and escape into the gas phase. Can these molecules down here escape? Not when they're down there. The people in the other Red Rover line who are not named Sally didn't get called to run across the field. They can't break through the line, right? Because they're not one of the surface molecules. Does anybody have any questions about that?
Can they move their way up?
Yes, they can move their way up. They definitely can. And there's a constant movement and recirculation and stuff. But at any given time, there are only so many molecules that are at the surface. Any other questions? There we go. Sorry for all the jumping around. Okay, so the average kinetic energy of the molecules increases with temperature. But that is an average. And within that average, you have some molecules that are lower in energy and some that are higher. And so here we're looking at a graph, fraction of molecules with this amount of energy versus the amount of kinetic energy. So at a lower temperature here with the blue line, we're going to have a bell curve, right? And we could figure out the average kinetic energy that's related to the temperature. But there's a distribution here. At a higher temperature, the average moves up, but in addition, the bell curve spreads out, the distribution broadens. And so what we're looking at here with this dotted line is this is the amount of kinetic energy needed for the molecules to escape. So we have to have this minimum amount of energy. If you have more, you can break through just fine, but this is how much you need to escape. So at a low temperature, we have only a small fraction of the molecules have enough energy to escape. When we increase the temperature, we have a larger fraction of molecules with enough energy. More molecules have the capability of escaping. And so vaporization will happen faster at a higher temperature. This is why when you have a wet towel and you want it to get dry, you stick it in the dryer, right? And the dryer heats the towel because that dries much faster than if you just leave it at room temperature. If you ever had the heating element on your dryer go out, you can know that if there's no heat in there, it has to tumble and blow for a long time before those clothes get dry. Another way to increase the rate of evaporation or vaporization is to increase the surface area of the liquid, because only the molecules at the surface can get through. And so there's some fraction of the molecules at the surface that have enough energy to escape. If we increase the surface area, then we have more molecules with enough energy and evaporation will happen faster. At the surface, those molecules are held less tightly because they have fewer neighbor-to-neighbor interactions. And then you can't escape unless you're at the edge. So what we observe is that liquids with stronger intermolecular forces evaporate more slowly than liquids with weak intermolecular forces. So we have two qualitative terms we use, volatile and non-volatile. Volatile describes a liquid that vaporizes easily, and non-volatile is a liquid that does not vaporize easily. So this surface area thing, that's what happens. That's why when you're trying to dry your hands under one of those annoying hand dryers in the bathroom, if you just stand there with your hands under there, it's going to take longer than if you rub your hands together. Because when you rub your hands together, you're continuously spreading the water around. You're maximizing the surface area of the water. Anybody have any questions? So if we think about that beaker and water is evaporating, and let's pretend that the beaker is thermally insulated, so we don't have to worry about any heat coming into or leaving the beaker from the surroundings. We're just going to look at the beaker itself. What's going to happen to the temperature of the water as those molecules evaporate? Well, which molecules are evaporating? The high energy ones or the low energy ones? The high energy ones, right? All the higher energy particles are leaving. What does that do to the average kinetic energy of those remaining? It goes down. So as the high energy molecules leave, the temperature of the liquid goes down. So it's a bit like, you talk about people and money, and you've got a community, and you've got poor people and middle class people and rich people. And for whatever reason, people start moving away, and it's all the rich people that can afford to move away. Well, what's that going to do to the average income of the town? It's going to go down, right? All the rich people left. And what you've got left are the middle and the poor people. That's what's happening here when a liquid evaporates. The high energy particles are leaving, and so what remains has lower kinetic energy. The temperature goes down. Vaporization is an endothermic process. This is why sweating cools your body. Because as your sweat evaporates, it's the high energy molecules that leave, and the ones that remain are lower in energy. And so unlike the insulated beaker, the sweat on your skin is not insulated from its surroundings, and so the sweat cools, and the heat from your skin will naturally move into the sweat, and so that cools your body. Condensation is an exothermic process, and that is not as obvious. So these state transitions, we need to be able to identify them as exothermic or endothermic. And so if you had a question on an exam and it's asking you about condensation and you're like, it's hard to think about. Well, think about the opposite. Think about evaporation. What makes evaporation go faster? If you heat it up or if you make it colder? If you heat it up, right? So if I put energy into it, it happens better. That's an endothermic process. So the opposite, condensation, must be exothermic. It's not something that's obvious to us. But when water condenses on something, it releases energy into whatever it's condensing on. So if you've ever been burned by steam, steam can burn you very, very quickly. And the reason is that as water in the gas state condenses on your skin, the heat of vaporization is very large, and so as it condenses, it releases a lot of energy into your skin and can cause a burn. We also see this in weather patterns. So I looked up some data comparing San Francisco and Fresno. And there's other things that you compare about those two cities, but we're just going to talk about temperatures here. So these are average daily temperatures in July from 1971 to 2000. So in Fresno, average high temperature 96.6. Be kind of a nice day. Low is 66.1 degrees. The difference in a day is 30.5 degrees. San Francisco, the average high in July, 68.2 degrees. The average low, 54.4 degrees. Difference, 13.8 degrees. In San Francisco, which is surrounded by water, the temperature doesn't go up very far during the day, and it doesn't come down very far at night. Because as the sun hits the water and all the moisture in the air and everything, the water absorbs that energy to go into the gas state. And then later, when the sun goes down and the air begins to cool, the water condenses and it releases that energy back into the surroundings. And so the vaporization and condensation of water moderates the temperature change. Fresno is in a natural desert. We don't have a lot of bodies of water. We don't have a lot of humidity. And so just like in, like the desert in Arizona, the temperature changes are huge in one day, right? The temperature changes more in a day in Fresno than it does from winter to summer in San Francisco. I mean, it's just really pretty crazy when you think about it. Why does the temperature change so much around here? Because we don't have a lot of water to absorb energy and release it back into the surroundings. Any questions about that? You've probably noticed there's always a week or two in the summer where it just doesn't cool down at night and it's just yucky, right? It's like, man, it only got down to 75 degrees last night. It was just miserable, right? It feels so humid. Well, that's when the humidity is higher. And that's when it doesn't cool down at night like it should. It should be 65 at night, right? In summer, yeah. You open the windows, you're like, oh, I can breathe. Maybe I can make it through tomorrow. I'm not a fan of hot weather. So, there's energy involved in vaporization and condensation. So we call this the heat of vaporization or enthalpy of vaporization. And it's symbolized as delta H, VAP. This is the amount of heat needed to vaporize 1 mole of liquid at its boiling point. So we can write a chemical equation to represent that, H2O liquid going to H2O gas. And so for that reaction, delta H is plus 40.7 kilojoules per mole of water. Heat of vaporization is always positive because vaporization is an endothermic process. It is somewhat temperature dependent. Here we're saying it's at its normal boiling point. Well, what would it be at another temperature? Well, in this table, here's water. There's the normal boiling point. Here's the heat of vaporization at the boiling point. Here's the heat of vaporization at room temperature. It's a little bit higher, but not really that different. And we've got a couple other compounds here. Isopropyl alcohol, that's what they swab on your skin to clean it before they give you an injection. And that feels cold, doesn't it, when they do that? It feels cold because that evaporates quickly. It's a volatile liquid. The heat of vaporization for that one is a bit less than for water, but at room temperature it's a little bit higher. And so one of the things that we did in that experiment we did on Tuesday, looking at the rates of evaporation, it had you look up heats of vaporization for these different compounds. And then you're supposed to compare the temperature difference that you saw with the heat of vaporization, and then also look at how that correlates with intermolecular forces. These are not numbers that you would memorize. You would either look them up in a table or be given those on an exam. So when a substance condenses, the same amount of heat is involved. It'd be really great if you could create heat by just vaporizing and condensing, but you can't, because conservation of energy, right? So when it condenses, it releases the same amount of energy that it absorbed when it evaporated. So we can write the opposite reaction, H2O gas to H2O liquid. Delta H here is the same, just change the sign. This is negative. So when you look it up in the table, you always just see the heat of vaporization. And if you need the heat of condensation, then you just change the sign. So this is a useful conversion factor between moles of substance and amount of heat involved in vaporization or condensation. There's not really a chemical equation that we use for this. Chemical equation. There's not a math equation like Q equals MC delta T. It's just dimensional analysis. Delta H, here's our kilojoules per mole. You got however many moles, and you can figure out the amount of heat. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Whenever you're not sure how to approach a problem, I recommend trying dimensional analysis first. So identify what do I have and what am I trying to find, and then we'll work on figuring out how to get there. Well, what am I given here? There's only one number, right? 2.58 kilograms of water. And they're asking me to find what? Kilojoules, right? For the vaporization. Like, well, vaporization. Oh, yeah, that's what we were just talking about. How much energy does it take to vaporize water? Well, there it is, 40.7 kilojoules for every mole. So that would be a useful number to have. Heat of vaporization plus 40.7 kilojoules per mole. And that's at the boiling point, and this is specified at the boiling point. So this is a conversion factor we're going to need. I'm trying to get from kilograms to kilojoules. I've got this heat that's going to allow me to convert between kilojoules and moles. So working backwards from the end, if I get moles of water, I can find the kilojoules using heat of vaporization. How do I get from kilograms of water to moles of water? Change kilograms to grams. And then can I go grams to moles? Yeah, that should be a piece of cake at this point. Molar mass of water, right? Any questions about the setup there? Dimensional analysis is not going to go away. It's just over and over and over in this class. So I've got my path, 2.58 kilograms. I've got 3 arrows. I'm going from kilograms to grams to moles to kilojoules. Always put the units in first, because people do weird things when they start sticking in the numbers right away. I'm not saying it can't be done, but I don't recommend it. All the units canceling out like they should. And remember, if you have kilograms on top and kilograms on top, those don't cancel out. You can cross them off, but that doesn't make it happen. So kilograms and grams, the relationship. What does kilo stand for? 10 to the 3. So in the bottom, I have 1 kilogram. On top, I'm going to write 1, and instead of K, I'm going to write what it means, times 10 to the 3 grams. And some of you are still a little shaky on some of these metric conversions. You've got the exponent right, but you're going in the wrong direction. Grams to moles, that's the molar mass of water. I'm not going to go over how you calculate that. And then kilojoules to moles, that's our heat of vaporization. That's not given in the problem, we have to go look it up. So 40.7 kilojoules for every 1 mole of water. 2.58 times 183 divided by 18.02 times 40.7. Just to be silly, I wrote down all the digits. How many sig figs should that number have? This is all multiplying and dividing. This one has 3. This is exact. We don't have to think about that one. 4 and 3. So this should have 3 significant figures. So we could express this as 5,830 kilojoules, or it'd be better to put it into scientific notation, 5.83 times 10 to the 3 kilojoules. Scientific notation isn't going away either, and neither are significant figures. On some of your experiments, I see people rounding off too much. I think maybe it's that you don't recognize those leading zeros aren't significant figures, and so you see a number that's 0.0005, and you oh, that's got 4 sig figs. No, it has 1. And you lose tons of information when you do that, and you get huge rounding errors, and you get the answer wrong. So if you're not sure how many sig figs to put in there, put more than you think. More is better than not enough, because you can always just chop the extras off at the end. If you cut them off too much, then you can get some serious errors that the only way to fix them is to go back and do the whole problem again. Any questions? Yes. Yeah. Yeah. So the delta H, you just look it up, or it would be given to you in the problem on an exam or on that sheet of useful information. 5.83 times 10 to the 3 kilojoules. So what if we have water in a closed container? Not an open beaker, but a closed container. So here we've got an Erlenmeyer flask with a stopper. Come on. Oh man, I think I killed my pencil. I dropped it on the floor again. Okay, so here we have an Erlenmeyer flask with a stopper on it. And so we've got water in here, and the water begins to evaporate. Because even at room temperature, some of those molecules have enough energy that they can escape. And so they begin to escape into the gas state. And then they do what gases do, and they travel in straight lines until they run into something. And so these molecules now in the gas state are going to be bumping around up here, and eventually they're going to collide with the liquid again and get trapped. That's condensation. So we have evaporation and we have condensation. So we have opposite processes occurring. Initially, all we have is evaporation. There's no condensation because there's nothing up here to condense. As we get more water molecules in the gas state, the rate of condensation is going to increase, because the more water molecules you have here, the more frequently somebody's going to run into the surface and get stuck. The rate of evaporation, though, is constant. That depends on the temperature and the surface area. And in this flask, the temperature and the surface area are not changing. So we have constant evaporation, and the condensation increases as the amount of gas increases. And at some point, the rate of evaporation is going to be equal to the rate of condensation. And that's called a dynamic equilibrium. The concentration in the gas state, the number of molecules in the liquid state are the same, staying the same. They're not changing. Not the same as each other, but they're not changing. But there's constant movement. Okay, sorry for the gap there in the recording. I don't know where I left off, but the point here is that the vapor pressure will be constant, regardless of the size of the container. Any questions? So let's test our understanding of that. What happens to the vapor pressure of a substance when its surface area is increased at constant temperature? Our choices are the vapor pressure increases, stays the same, or decreases. Well, how do we even go about thinking of this? So here we have, I had to break up my finger again. So this is our liquid here. And we're going to put this in a different container where the surface area is larger. How does changing the surface area affect the rate of evaporation? It would increase, right? Because there's more molecules at the surface. You have to be at the surface to escape. Is increasing the surface area going to affect the rate of condensation? Yeah, it will, because here you have a small area for those gas molecules to run into. Here you have a larger area for the gas molecules to run into. So the rate of evaporation is going to go up, but the rate of condensation is also going to go up. And so the effect is that the pressure here is going to remain the same. Okay? You can't change the vapor pressure of a liquid just by putting it in a different shaped container. This is why when we collected gas over water, Dalton's law of partial pressures, and we subtracted the vapor pressure, that's why we can just look up the vapor pressure of water in a table, because it only depends on the temperature. The surface area doesn't matter at all, because the surface area affects evaporation and condensation.
So instead of it being at a constant temperature, if it was at a higher temperature, it would...
If you change the temperature, then you're going to change the vapor pressure. Yeah. If you heat the liquid, it evaporates more easily, and so you're going to get more gas pressure. If you cool the liquid, the vapor pressure is going to go down. But this is at constant temperature. Any questions? So there's a relationship between temperature and vapor pressure. Here we've got the vapor pressure in torr of several different liquids as a function of temperature. So here along the red line is our friend water. And we see that, down at room temperature, the vapor pressure of water is very small. But as we heat the water, it goes up significantly. And at 100 degrees Celsius, the vapor pressure of water is equal to the atmospheric pressure. Other liquids with different intermolecular forces are going to have different vapor pressures, but they all show the same trend where if you heat them, the vapor pressure goes up. It doesn't go up necessarily in the same way. It's not a linear relationship, but it always goes up when you heat them. You can have a large change in vapor pressure from a small change in temperature, depending where on this curve you are. Now, ethylene glycol, its vapor pressure doesn't change very much at all. But diethyl ether, you get a 5-10 degree increase in temperature and the vapor pressure goes way up. The boiling point of a liquid is the temperature where its vapor pressure is equal to the external pressure. So here in a pot of water boiling on the stove, the external pressure is 1 atmosphere, right? Normal atmospheric pressure. As we heat the water up, the vapor pressure increases and increases and increases. When it gets to 100 degrees Celsius, the vapor pressure is such that bubbles of gas will form inside the liquid. And of course, they're not going to stay there because they're less dense. They're going to rise to the surface. But that's what boiling is. So we've got gas bubbles forming within the liquid because the vapor pressure of the liquid is equal to the atmospheric pressure. The molecules in the interior of the liquid have enough energy to break loose. And so they're going to break free of their neighbors and form little pockets of gas. The normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. In other words, the temperature at which it boils at normal atmospheric pressure. If we change the external pressure, we change the boiling point of the liquid. You've heard of Instant Pots? You know what those are? Those are the new variety of pressure cookers. In the old days, your grandma or great-grandma used to use a pressure cooker, and those things are kind of dangerous because they exploded occasionally. But an Instant Pot is an electric pressure cooker. It's got a lid that clamps on, And you have to have liquid water in there. You can't just, put a dry piece of meat in there. You have to have some water in there. It heats up, the water begins to boil and creates steam, gas, which increases in pressure because it's sealed from the outside. So you're heating up a closed container and the pressure is building up. Well, at a higher pressure, the boiling point of water is lower. If we go back to this. So here's the result of the right side there, and I want to keep extra sig figs. Let's see what happens with the units. Here's joules canceling with joules, and moles canceling with moles. And here I have 1 over Kelvin, and here I have 1 over Kelvin. The kelvins cancel out too. So I end up with no units on the right side, which is as it should be. So the natural log of P2 divided by 1 atmosphere is equal to that number. The opposite of natural log is e to the x. And so I'm going to take e to the x of both sides, e to the x of natural log equals e to the, well, not e to the, e to the 2.2. I didn't really write this correctly over here. Let's fix this. This is e raised to this power is equal to e raised to that power. Well, the e to the x and the natural log cancel each other out. E to the 2.22 blah 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 is equal to 9.266. And that is equal to P2 divided by 1 atmosphere. So P2 is equal to 9.26643 atmospheres. And we go to look at the answer, and it gives it in torr. Okay, well, we can convert this to torr. Just multiply by 760. So in torr, I get 7042.49 torr, or 7.04 times 10 to the third torr. Any questions? So when you took e to the 2.226399, you got a different number? What'd you get?
It's not too far off, but it's 9.265.
Well, I used the unrounded. I just went up and pulled the number from the register. So, yeah, if I use it as written, no, I get 9.26643. Something very interesting happens if we vaporize a liquid in a sealed container with heating. So, in theory, you could do this in your Instant Pot at home, but actually you can't, because the thing would, hopefully the safety features would override that before it got to a high enough pressure. But in the correct sort of apparatus, what happens is, as the temperature increases, so does the pressure. And the pressure makes the gas become more dense, the liquid becomes less dense, and at some point they merge together. You don't have gas or liquid, you have something that's in between a gas and a liquid. And that's called a supercritical fluid. It's hard to get a picture of it. This is looking into a chamber. Here we see the liquid and the gas. And here the liquid's boiling, and they're beginning to merge together, and after a while we get this supercritical fluid. There's only one state. It's not a gas, but it's not a liquid either. Supercritical fluids will exist above the critical temperature for whichever substance you're looking at. Above that critical temperature, a liquid cannot exist. The pressure at that transition point is called the supercritical pressure. Supercritical fluids, because they have such interesting properties, are very useful as solvents. So supercritical CO2 is used to decaffeinate coffee. So we can use supercritical CO2. It's not a gas, but it's not a liquid. And the caffeine in the coffee will dissolve in the supercritical CO2, and you can flush it away, but the flavor and all the other good stuff in the coffee does not dissolve in the CO2. And then after you've washed away the caffeine, you release the pressure, and the CO2 just goes into the atmosphere and leaves no residue behind. So it's like a really awesome process. Although why you would want to take the caffeine out of coffee, I think that's the only good part of coffee. Any questions?